Hi, we'll talk about partial derivatives, then we'll talk about the chain rule, we'll talk about Hessian, we'll talk about Jacobian, and try to relate where it is all used in machine learning. Okay. So there are a lot of equations here, we'll just go one at a time. Okay, don't worry about it. So we'll start with the simplest of one. F of x is equal to x squared. This is the the function we are most used to. Okay, what does it say? The derivative dy by dx is equal to 2x. Very simple. It is a univariate function, which means that the output y depends only on the one input, that is x. So if it is a graph, the output y is the output of the graph. It depends only on x. So when x changes, y changes. That's the simplest equation. And any change to this x will correspondingly give a derivative dy by dx, that is 2x. That is univariate. So that is the simplest form of equation which we come across. But practically, life is not that simple. We will deal with a lot of equations with multiple variables. Then we get into what we call as multivariable calculus. So we'll erase this because this is the simplest one, univariate stuff. Okay, which we all know. Now let's move on to this function. Okay, this is a function which depends on two variables, x and y. So this is called multivariable, where the output of the function depends upon two variables, that is x and y. So any change to x will impact y, any change to y will impact y. So any change to x will impact this function f of xy, any change to y will impact this function f of xy. So there are two variables. So practically a lot of our problems in machine learning or any engineering problems will have multiple variables which impacts the output. Let's take an example of house price. It depends upon the number of bedrooms, the location of the house, the proximity to transportation, proximity to schools, safety of the locality. Okay, so all this is in consideration when we take into consideration when we find the price of the house. So any of this variable has a different value, and if it changes a little bit, the output reacts to it. Okay, so that's why we call it as multivariable calculus. Okay, so we'll go into detail about this. Next, this is an example of multivariable. So this is an example of univariate calculus. This is an example for multivariate function, and we'll get to multivariate calculus. And we'll also see this actually, okay, where there is a dependency of z on two variables x and y. See, z depends on x and y. X depends on t, y depends on t. So which means that there is a relationship between multiple functions internally, okay, to get the output. So this is the simplest form of one of the such functions. Okay, we'll talk about this and come back here. So this is a function where you have x as an input. Okay, and if you take a derivative of this x, that is f dash of x, it becomes 3 into x squared plus 1, and then you have x squared inside as well. So we need to take the derivative of that, and becomes 2x. This is called what we call as chain rule. Okay. So when you take a derivative, you let's assume that this is the entire x plus 1 is something like x, and you have just cube. What you do is you take 3 here, and it becomes 3x squared, right? That's how you do when you have just x cube. Okay, it becomes 3x squared. Similarly, you take 3, and then this becomes x plus 1, x squared plus 1 the whole square. Actually, this becomes x squared plus 1 the whole square. And after you do that, there is an x term inside. So we need to take a derivative of this x term also, and it becomes dot 2x. So this is the derivative of this function x squared plus 1 the whole cube. So 3 comes before, x squared plus 1 the whole square. So just like this, x cube becomes 3x squared, this becomes 3x squared. And you have one more term inside, that is x squared plus 1. You need to take the derivative of that, and that becomes 2x. This is what we call it, the chain rule. Okay, so when you have dependent functions, we need to take and expand it and take the derivative of the function outside and also the function inside. Similarly, this is a more complex one. This is a simpler one. This is a more complex one. So let's draw it actually. Z depends upon x and y, and x depends upon t, and y depends upon y depends upon t. So when we have variables, when you have multiple variables, like here we have multiple variables x and y, and this is also an x and y. When we take derivatives of such functions, we call it as partial derivatives. Why do we call it as partial derivatives? So in case of the I mean like univariate calculus, if I mean x just depends upon only one I mean output just depends upon a single variable x. So if it makes a change in x, the output y is directly dependent on it. That is called univariate calculus. Now, when we have more than one input variable, let's say in this case, let's take this case again, um, x, y, and this f of x, y. F of x, y, we will call it as z. So when we have two variables that impacts the output, a small change in x makes an impact on z, that is the function f of x, y. A small change in y makes an impact on z, that is f of x, y. So when we try to find derivatives of such functions which is dependent on x and y, we take a small change in x and treat y as constant and then take the derivative. Similarly, when we take derivative of y, that is the impact of z with respect to y, we make a small change in y and treat x as constant. That is how we take derivatives of this. Okay. Now we will use this example and take the derivatives, partial derivatives. That's what we call as partial derivatives. Okay, then once we are done with this, we'll come back to this function. So let's take the partial derivative of this function. So we used to have derivatives defined as dy by dx, and now it is going to be df1 by dx. This becomes the symbol changes from d to delta or del. Okay, so this is the partial derivative of this function with respect to x, and similarly the partial derivative of this function with respect to y. So what it means is that when you take a function, the partial derivative of this function with respect to x, you treat y as constant. So this becomes 6x squared. Okay, this becomes 6x squared. This is constant, and this becomes you treat y as constant, so it becomes 4y. Okay, this one becomes partial derivative of this function with respect to y. So we treat x as constant. So this becomes 0, and this becomes minus 8y cubed 8y cube plus x becomes constant, so it becomes 4x. So this is how you take partial derivative of this function. F of x y is equal to 3x squared minus 2 y to the power of 4 plus 4xy. Derivative of the first function, the function with respect to x, the function with respect to y. This is called partial derivative. When you treat when you take derivative with respect to x, you treat y as constant. When you treat derivative with y, you treat x as constant. So this is your first order partial derivatives. Now let's use this and try to see what happens here. Now if you wanted to find, this is a nested function. Okay, this is a simple xy function. This is a nested function. So what happens here is you wanted to make a small change in t, and you wanted to find what is the impact on the of the t to z. So this becomes, okay. Let's draw this. Let's draw all the route. Dz depends on x, so this becomes delta z by delta x. Then here x depends on t, this becomes delta x by delta t. Similarly, this side it becomes delta z depends on delta y, and here delta y depends on delta t. So there are four partial derivatives. If you combine together, you will find the impact of dz divided by dt, which means I'm making a small change in t. What is the impact of it on z? I'm making a small change in t. What is the impact on it on z? I'm making a small change in t. What is the impact on z? So I cannot directly go from here to here. I'll have to calculate the intermediate derivatives or partial derivatives, and then go here. So this derivative overall it becomes dz by dt is equal to, we need to multiply these two derivatives and add. So it becomes dz by dx, that's this path, dz by dx, and then dx by dt into dx by dt plus dz by dy into y by delta. Okay, this is the partial derivatives of 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 this function. Okay, the change in t on change in z. Okay, so dz by delta z by delta t. Okay, this is the overall equation. Okay, so if you try to find the partial derivatives of this, of these two components, 1 2 3 4, and try to multiply and add it, you will get this is what we call it as a chain rule. Okay, using partial derivatives. So we'll recap. We started off with a simple function f of x is equal to x squared. The derivative was straightforward, that is dy by dx, okay, is equal to 2x. Because it just varies on just one single variable, we got the output 2x, no issues. Now we move on to a function which is more complex. Let's take this function where you have a function x squared plus 1 the whole cube, and you have, if we try to find the derivative of this, you find the derivative of the outside function, that is 3x squared plus 1 the whole square, this becomes this, and then you have a x square component inside, so you need to take derivative of this, it becomes 2x. This is like a chain rule on a function which is of this form. Now if you have a function which has got multiple variables like x and y, when you take a derivative, we call it as partial derivative, or you can call it as dou f by dou x. Okay, and you need to take the derivative of the first function with respect to x, sorry, the function with respect to the first variable x, and the function with respect to the second variable y, by treating the other one as constant. Okay, so that is how you can find the impact of the changes. Okay, and this is what we call it as partial derivatives. So when you try to apply these partial derivatives onto more complex functions like this, which is nested, then you will have a kind of if you wanted to find out the change in z when I make a change in value of t, then you can draw a diagram like this, like z x t z y t, because it is the z depends on x and y, z depends on x and y, and then x depends on t, x depends on t, y depends on t, so y depends on t. So you can draw a diagram like this and try to find out how many partial derivatives you need to find out. Okay, partial derivative is nothing but the way you found out here. Okay, let's take one example and try to find out the partial derivative of the first one, dz with respect to dx. So dz with respect to dx. Okay, so let's say this, when I say dz with respect to dx, you treat y as constant, so this becomes 2xy. Okay, 2y as constant, so it becomes 2xy, and into dx by dt, x by t. So which means you're taking the partial derivative of x with respect to t. This becomes 3t square. 3t square. Okay, plus dou z by dou y, which means I'm taking this with respect to y. So I'm going to treat x squared as constant. So this becomes x squared. Okay, and this becomes 2xy into 2xy. So this is the first derivative of dz by dt. This is like, if you try to add these two, you get this is the derivative of this. This is the partial derivative of this nested function. Okay. I think there is one small correction here. It should be 2xy plus y square, because it's like we're taking dz by dx. It is like 2xy and plus y square. This is x, this is plus y square, and here it would be when you take dz by dy, it should be like x square plus 2xy, and this t square becomes, and I mean dy by dt becomes 2t. So yeah, that's, I mean, the calculation not so important, but the idea is this actually. You have a univariate, I mean univariate function, you do an univariate calculus. When you have multivariate function, we use partial derivatives to kind of get the impact of a particular change on the output. Okay, so this is called what we call as partial derivatives. Now we talked about this. We'll erase this. We talked about this function. We'll erase this. Okay, and we talked about this. We'll erase this. Partial derivatives. We'll erase this. And we want to extend the concept of the partial derivatives to one more level. Okay, so we had a function which we took a partial derivative of f with respect to x, and the function with respect to y, which is the partial derivative of this function, multivariate function. Okay, now if you try to do this derivative one more time, okay, which means trying to take the second derivative of this function, that becomes um, okay, let me change the pen. So it becomes, this is the second derivative of this. Okay, this is the second derivative of this equal to, again you're taking this function with respect to x, so it becomes 6x squared plus 4y. It becomes, yeah, I have written the original function back so that, okay, we kind of see where it's coming from. If you take the first derivative, it becomes 6x squared plus 4y. Oh, sorry, it should be 6x plus 4y. Okay, so this is 6x plus 4y, and the second derivative is minus. Okay, this is the first derivative. Now, if we try to take a second derivative of this function, it becomes 6x6 actually, because this becomes constant and becomes 6. So this function is first derivative, and this is the second derivative. Similarly, if you take the second derivative of this with respect to y, this becomes constant, y becomes constant, sorry, x becomes constant, it becomes 0, and this becomes minus 24 um, y square. Okay, so this is your second derivative. Now there is one more derivative when we talk about the second derivative, that is treating derivative of the function first with respect to x, then with respect to y, and derivative of the function first with respect to y and with respect to x. So this is another derivative. So which means that we have taken the first derivative df by dx, or dou dou y, and this is the second derivative, first derivative, second derivative, and this is one more derivative. It's not a third derivative, but it's like it's like trying to treat um, first with derivative with respect to x first, then with respect to y. Okay, so here we are continuously taking derivative of the x, then we are taking the second derivative also with respect to x. Now instead of taking the second derivative with respect to x, once you take the derivative with respect to x, and the next you take it to y. So this becomes 6x plus 4y. Okay, this becomes, first you have taken with respect to x. Now if you take with respect to y, this becomes constants, and this becomes 4. Okay, this is the second function with respect to, if you take first with respect to y, that's what it is, then you take with respect to x, this becomes a constant, it becomes 0, and this becomes 4. Okay, so this is extension of the derivatives. Like we started off with the partial derivatives, and then the partial derivatives to second order partial derivatives, and then the derivative when we take with x first, and then with y, and y first, and then with x. Okay, these are derivatives. So why do we do this? Um, when we want to quantify a particular a change of a particular function with respect to x and y, and if you try to capture everything, what we call it as a Hessian matrix. Okay, if we call it as a Hessian matrix, that is denoted by the function with respect to x, second derivative of the function with respect to x, then second derivative of the function with respect to y. Okay, that is the diagonal, this diagonal, and this diagonal will have second derivative of the function with respect to y, second derivative of the function with respect to y, and then with x. This one will have x first with x and then with y. So if we try to populate these values into what we call as an Hessian matrix, you will get h is equal to, okay, we have all the values out here. So this is the first derivative, second derivative with respect to 6. Okay, this is df by second derivative of this with x. This is 6. Then you have first with x and then with y. First with x and then with y. This is 4. Okay. Next, this one. Sorry, this is here first with y and then with x. First with y and then with x. This is 4. And then you have second derivative, which is minus 24 y squared. Okay. This is what we call it as a Hessian matrix. So Hessian matrix is used when we try to deal with higher order derivatives, okay, and particularly second order derivatives. And if you wanted to, if you have one more variable called z, you will have one more column and one more row, which is meant for z. So if you have n number of variables, you can expand this and represent the Hessian matrix in this form, okay, and you can take all the partial derivatives of this equation and plug it into this matrix, okay. Okay. Okay, I talked about Hessian matrix and where it is used. It is used with higher order derivatives, second order derivatives, and so on. So where it is used in machine learning, when you use Taylor series to approximate a polynomial, we deal with higher order derivatives, and that's where it's used actually. I'll give an example. Uh, that's what I have written on the other side, okay, which we saw in the Taylor series. We'll expand that and see what happens. Okay, so if you had seen the video of Taylor series, what it means is that if we have a cosine function or cos function like this, okay, this is the cos function. This is the cos function. You can approximate that using a polynomial function. Okay, the polynomial function like 1 minus x squared, 1 minus 1 by 2 x squared approximates this cos function like this. So it will touch this somewhere close here, and it will go here. It will touch exactly and and go like this. So what we're trying to say is you can use a polynomial function like this to approximate a complex trigonometry function, because polynomial functions are easy to work with, easy to take derivatives, and easy to approximate compared to this function. So we're trying to approximate this when we try to approximate this polynomial function. Sorry, this trigonometry function of this polynomial function, we use higher order derivatives in Taylor series, and Hessian matrix will help us to kind of collect all the derivatives. So how does it work actually? So in this case, cos theta is equal to this is the cos wave. Okay, cos 0 is 1. Okay, cos 0 is 1 at x is equal to 0, cos is 1. Okay, so the first order derivative, I mean, if you take a polynomial equation, it will be like this actually. C0 plus C1x plus C2x squared. Okay, this is an equation. This is a polynomial equation of degree 2. So we're trying to approximate this function with this. And what you see here is at cos cos 0, the value is 1. So this can be at x is equal to 0, this is 1. Okay, so it becomes 1 plus C1x, or everything becomes 0. Okay, that is the first at x is equal to 0. Now, now the next is like we found the first term. The next term is we wanted to find equation such that the slope is 0 at this point. Okay, so which means the slope is 0. So the first derivative of this cos theta has become sin theta. Okay, sin 0 is 0. Okay, so sin 0 is 0. So which means that um, this This is the first order derivative. If you put a C1 as 0, the first derivative will become 0. So this becomes 0x if you take the first order derivative. And next, if you expand this to the second order derivative, like the first derivative is the slope is 0, we got it. The second derivative is like the slope after that, okay, it kind of becomes negative. So if you wanted to have a slope which is negative, this again sine theta becomes cos theta, and this is the second derivative. So this is like this is the first derivative, d f by d theta, okay, and here is d square f by d theta. So changing theta here. So if you want to try to find the second order derivative here, this becomes we need to find out the value when it becomes I mean like minus 1 by 2. So we need to substitute here actually 1 plus 0x. The second order derivative should be we need x to be minus 1 by 2. Okay, so that the value becomes minus 1 at x. Okay, so this is how we kind of use this Taylor series to approximate. So this is how we match it. So we have negative here. Sorry, the derivative of cos theta is minus sin theta. So the second derivative will again be minus 0, it will become minus 1. That's the reason we are trying to find out the value. When you, at the second derivative, if you take it, this becomes um, 2x, okay, and this will get cancelled and become minus 1. So the second derivative or the second slope becomes minus 1. Okay, so that's how we try to match this equation with this. And when we deal with higher order derivatives, this Hessian matrix will take. Okay, so this is the history of why we're using Hessian. Okay. So far we have seen functions with a single variable, then with multiple variable. Then we have seen functions, I mean, if it is multiple variables, you take partial derivatives of the functions so that you'll be able to form the gradient, okay, matrix or the gradient vector or the Hessian matrix. Okay, so there is one more concept which is called Jacobian, where you take instead of two variables as an input, you take two functions as an input and produce two functions in output. Okay, this is how it is actually. You take a function x, function xy, and it has got two functions in itself, which is like f1 and f2, and it outputs a function which is again like this. So what does it this Jacobian do, or why is it useful? When we take a matrix as an the purpose of the matrix in linear algebra, it takes care of the linear transformation, okay, from a point A to B. When you do like transformations which are not linear, okay, in this case, like when you take a complex linear transformations of multiple, like let's say in a neural network, okay, it's no longer linear because it's I mean it's like you have curvy functions which is kind of approximated. Even though we do that, okay, even though the function kind of is not linear at the large scale, if you zoom into certain parts of the transformations, okay, let's say the function transforms something like this, okay, and if you try to zoom in a particular point, okay, let's say a small area, and try to find a transformation at this particular point of any variable that looks to be linear, locally linear, okay. So this Jacobian matrix is used to kind of take care of those I mean representation of the linear transformations happening at those small local areas which is linear. Okay, and that's, I mean, any matrix, it's used to kind of transform a matrix, I mean, or vector from a domain to codomain. Okay, that's what the matrix is. And in case of Jacobian matrix, what it does is it just does the same in the neural network, where you do not have the overall transformation is not linear, because neural network by nature is not, it can approximate any function. But when you try to look into a certain zoomed in area of the transformation, that looks to be linear, okay, and that representations can be done using Jacobian. So how does it work? Okay, so you have a function like this, which is like an input, which x and y, and you have to take the derivative of the functions like this, actually derivative of the function first function with respect to x, the second function with respect to y, sorry, second function with respect to x, okay, and the second function with respect to y, and the second function with respect to first function with respect to y and second function with respect to y. So basically, the first row corresponds to first functions, the second row corresponds to second functions. The first function is taken derivative with respect to x first, then y. The second function is taken with derivative with respect to x first and y next. So this is how inputs which is not linear. I mean, like the transformation is not linear or on the larger scale is represented using a Jacobian matrix for transformations which are locally linear. Okay, so this, if I mean, this is an example. If you take the derivative of this, what I have just extracted the results here. So this becomes the Jacobian matrix. So for any point x and y, if you try to plug in here, you will get the linear transformation of the particular point. So where it is used is in neural networks where you have multiple nodes. Okay, let's say you have nodes. This is an input, and this is now this is intermediate nodes, and you have an output. Okay, and you keep doing matrix multiplication. The input is multiplied by the matrices, which is like the weights. Okay, and you get the output. Okay, and when you do that, this Jacobian matrix is what helps us to kind of collect all the partial derivatives with respect to each functions, and then you can directly multiply these matrices like 1, 2, and 3 in the order. Okay, so that it kind of captures all the intermediate transformations, and you will get the output. So we didn't talk detail about linear neural network yet, but just assume for now. Okay, we had an example like 1 into 2 is equal to 2, 2 into 2 is equal to 4, and we wanted to find a function which is like with what if I multiply x, I will get 4. So we are trying to approximate this function 2x, or try to find the function 2x using a simple linear model. Okay, that's how the machine learning example we started off with. Now instead of having just one variable to guess, okay, we just guessed initially 1, then we added value 2 and found the multiplication results. So instead of just having one variable to work with, okay, if you have multiple placeholders to kind of guess and multiply things to get the output, that is the fundamental idea of neural network. So let's say you have the input 1. Okay, instead of trying to find, okay, with what if I multiply 1, I will get 2. Okay, instead of having just one placeholder for multiplying, let's say I have a placeholder here where I can multiply with 0.1 here, like 0.2, then 0.3 here, and I can go in sequence. Okay, and eventually I try to find out the value or the answer as 2 here. Okay, and try to find out this function. So if you have more nodes and if you have more placeholders to kind of do the multiplication, and you can expand it like this, and you can expand it like this. So when you start growing this placeholders, you call it as like a multi-layer neural networks. Okay, where I mean just giving an intuition. Actually, it's not exactly the way it is I'm representing, but I'll give an idea of okay why we are trying to use matrix to kind of represent these transformations, and why Jacobian matrix because it is going to deal with main inputs which are going to go through multiple linear transformations. Why partial derivatives? Because earlier we just directly said, okay, if I wanted to find, if I find the error is 2, sorry, if I had the initial guess as 1, okay, 2 into 1 is will be 1, the error is actually 1, okay. Now I wanted to reduce this error. Now if I do, I just had only one placeholder here, so I was able to do a kind of check between difference between 2 and 1, and I was able to update this to like 1.5 and 2, and eventually reduce the error from 1 to 0, because we just had one placeholder. Now assume that you have multiple placeholders like this to multiply, and directly the input, whatever you make a change here is not reflecting there. Yeah, and if you want to back propagate the error, okay, and try to reduce it, then that becomes a series of transformations in between. And in order to find out the impact of a small change in the output based upon a small change in input, then that becomes a network of nodes which has to kind of deal with the partial derivatives, and that's the reason we're using partial derivatives. Remember, I just give an example. Like we had a function z which depended on x and y, and this depended on t. Okay, and we have to find the partial derivative of dz with respect to dx then dx with respect to dt, and we had to multiply this to find the impact of dz with respect to dt. So we had to multiply this. Similarly, just put it this way. Okay, let's just flip it around. Okay, this is z, and it depends upon, let's say, x and y, and it depends upon p, two inputs. Then this becomes dz with respect to y, this becomes dz with respect to x, and this becomes dx with respect to dt, which means that for small change in t, what may change in x, and with small change in x, what may change in z. Okay, similarly, this becomes dz um, dy divided by dt. So if you see here, these are the inputs, and if you make a small change in input, I wanted to find out the corresponding impact on the output, and I do multiply all the partial derivatives out here to get the impact of the change. And if the error is large, accordingly I change my direction to reduce the error and try to reduce it. Similarly, that's what is happening here. If you wanted to find the multiplication table, 2 into what gives me 2, and if you have multiple nodes here, okay, instead of just one variable to guess, if you have multiple variables and I have to pass through in sequence, then if I make an error, I'll have to come back in the same sequence. This is the sequence I'm talking about. So that's the reason you have a lot of partial derivatives here, because it is not like one on one. Okay, x does not depend directly on one input. I mean, y does not directly depend on one input. It has branches and it has multiple dependencies. So that's the reason we use partial derivatives to kind of capture all the like all the small incremental changes at every nodes and at every points. And in order to represent all these changes, we put it all into a matrix like this Jacobian. So assume that we have series of Jacobian matrix which takes care of the partial derivatives out here, and we try to do the back propagation. Yeah, we'll see neural network in detail later, but the intuition is the same. Just having multiple placeholders to keep this multiplication, to kind of capture the notion of partial derivatives and make it more useful to represent using matrix. So yeah, this it's quite overwhelming video. We talked about partial derivatives. We talked about then chain rule. This is chain rule basically, and we talked about the use of Hessians, okay, for approximating higher order derivatives for in Taylor series, and we talked about Jacobians for making use of it to represent partial derivatives in the neural networks. Okay, so yeah, thank you.